For this section, we are going to be talking about things called the complex and imaginary numbers, which I'm hoping you have some familiarity with already, but more realistically, I understand that a lot of you are probably already feeling your eyes start to glaze over, because when you hear the names complex and imaginary numbers, you're probably thinking, what the hell, man? Math is already weird and made up. Both of those things are actually true, but I probably shouldn't tell you that. Shh. So why do these have to be the things that we call complex and imaginary? Well, to try and understand that, I'm going to give you guys a bit of history. So the term root, the term that all of this stuff is built off of, comes from the Latin word radix, meaning base, that comes from a mistranslated Arabic word of roughly the same meaning, where base is taken to mean something more like basic than a place you might want to hide. What we mean is taking something and breaking it down into its basic components, like how a square root breaks something down into parts. And we'll see that this term comes up again later in the context of radicals in a little while. But that's the idea we're building from, that a root is something like finding your basic pieces. So, to put it in the context of a quick example for the type of thing that we'll see in the next section, if we're talking about something like x squared minus 4x plus 3 equals 0, the act of finding the roots is the act of finding the most basic parts of this thing, which we could do by factoring, but I'm not going to write out because those are concerns for when we get to 1.4, and hopefully you guys at least know a little bit about that to know that what we're going to get here would be the values for x of 1 and 3. Those are our roots. Those are our basic pieces, thinking in terms of the radix, as it were. So if you want to think about a square root, you can talk about a square root as specifically being the thing whose basic parts are the same value and itself, one thing twice. So if you want to break down a thing more like, say, x minus 2 squared equals 0, which you could pull out, and that would end up being x squared minus 4x plus 4 equals 0. Well, the root, the basic piece, would be x equals 2 twice. Sometimes roots happen more than once. And again, we'll talk about that stuff more as we're going on, just giving a bit of sense as to what it is that a root really finds, in a sense. However, the square root is and was designed for dealing with positive things, but we don't always get positive things, right? You know, a square root by our math should be identifying a thing multiplied by itself, and if you multiply anything by itself, it can't become negative. That's how the negative numbers are defined, that's how multiplication is defined. So if we have something instead like x squared equals negative 1, we have a problem, because x squared equals negative 1 tells us that we need to find the basic piece that you can take with negative 1 twice to get there. And that sentence doesn't make a whole lot of sense, but neither does this equation, because this isn't a value. It's not a value in terms of the real numbers as we understand them, and it actually wasn't a value in terms of real numbers as we understand them in the time that these sort of operations were being formalized into the way we understand them. In particular, the work that formalized a lot of this stuff to the way we have it now is a return from our friend earlier on in here, Descartes, in his same work that we referenced last time from the 17th century, where in particular when he was talking about this kind of equation, that kind of value, he said that these quantities are, via translation, sometimes only imaginary, That is, one can imagine as many as I said in each equation, but sometimes there exists no quantity that matches that which we imagine. And so, because on the day when René Descartes was working on this stuff, or he was publishing it, he was feeling a little bit snooty, a little bit arrogant about what these things represented, he gave them the name imaginary numbers. That's where we get the notation that I, the square root of -1, is defined as the imaginary unit. Because in Descartes' time, and in Descartes' work, the idea was that the real numbers, they did enough. So the fact that we had these imaginary things chasing around didn't tell us that there was more to understand. It told us that, hey, our equation has gaps in it. But just because it has gaps doesn't mean that those gaps matter. To put it a bit more bluntly, according to René Descartes, these square roots of negative numbers were fake news. However, just because he thought they didn't matter doesn't mean that they actually don't matter. And in fact, the work of other mathematicians over the next couple of years, 100 years, not quite that quick, although it'd be cool if it was, in particular work by Leonhard Euler and Gauss over the next few hundred years, would show much more use for these things. And in particular, in reference to what Descartes has said, and to Descartes' notation in particular, Gauss responded, "We must admit with humility that while number is purely a product of our minds, space has a reality outside our minds, so that we cannot completely prescribe its properties a priori, and that this subject has hitherto been surrounded by mysterious obscurity is to be attributed largely to an ill-adapted notation. If, for example, +1, -1, and the square root of -1 had been called direct, inverse, and lateral units, instead of positive, negative, and imaginary, such an obscurity would have been out of the question." Now, there's a lot to unpack there in some very catty academic discourse. But basically what Gauss was saying in that first part is that just because we don't understand what something does yet, doesn't mean we should assume that it doesn't do anything meaningful. And in particular, his argument was that the imaginary numbers did do some very useful things. And they, in fact, do very useful things. We're not going to see all of them, but these are still things that are studied to this day in some very strange and unique and interesting manners. And for that second quote, not only does that say a nice thing about the imaginary numbers, which I'll talk about in a second, but I like also thinking about the positive and negative values in the way that he did. Because if you think instead of positive, that I am, say, coming towards you to give you something, and instead of negative, I could say I am taking something and going away, I think it's a bit clearer about how those things work. And for that matter, instead of calling the imaginary things imaginary, that they just appear out of thin air and mathematical convenience, they are instead something that is doing an important thing, but it's an important thing that doesn't involve you. So, I guess it wasn't quite so self-evident in this case for Descartes, but we can't be right every time. Hello from the editing room, everyone. I know this video is already probably a bit longer than I normally like to make them, but there's something very important in here that I want to mention that I forgot to put in there as I was shooting. So, a lot of the modern math notation we work with, and especially a good chunk of what we see in this class, comes from the French, and in particular, Descartes, where a lot of it is very good and sensible, but that's not always going to be the case. So, something I always like to tell my students, and I should definitely have made time to tell you in there, is if you're ever looking at something and you see it, you just go, why did they think that was going to work? Why did they think that was a good idea? Why is it written this way? Well, you can generally blame the French. Anyway, back to the rest of the video. In any case, the next thing we're going to look at is, after all this academic discourse, a bit about how these values actually work and interact.